Hello, we're back to look at angular momentum, this time of a solid spinning object. In the last video, we saw that angular momentum of a point particle, or an object that can be treated as a point particle, is L for angular momentum is equal to R cross P, which is the cross product of the radius vector and the momentum vector. We also saw that in practice, this formula is most useful in the form RMV sine phi, where R is the radius vector, the magnitude of that, M is the mass, V is the magnitude of the velocity or speed, and phi is the angle between the radius vector and velocity vector. In this lesson, we will consider a single solid spinning object. For example, let's consider a compact disk, a spinning compact disk. We isolate one single mass element on the compact disk. This mass element would be at Ri for the radius of that single element. I just learned that compact disks spin clockwise, so we can also add a velocity vector at a right angle for this particle. This would be the velocity. We can calculate the angular momentum of that single mass element, and that is angular momentum L is equal to R, which is the radius vector, usually in meters, times M, that's Ri, times M sub I, which is usually in kilograms, times V sub I, which is usually in meters per second, multiplied by the sine of phi, where phi is the angle between the radius vector and the velocity vector. All particles will have phi as 90 degrees here, so sine of phi is going to be sine of 90 degrees, or 1. So we will have L, angular momentum, equals Ri, Mi. Now, V sub I, we're going to substitute the rotational value in for the velocity. And what is that? That is omega R, omega angular velocity times the radius vector. So the individual particle has mi Ri squared omega I angular momentum. What is the angular momentum of the entire compact disk? Now, a long time ago, somebody had the idea that when you take a solid spinning object, you should capitalize the L. It's customarily done, so I follow the custom here. Angular momentum of the entire disk then would be summation of all of these, Ri squared omega sub I. And that is for I from 1 to n, all those particles. Think back. What is this quantity here? What is mr squared? Do you remember what that is? If you remembered I for rotational inertia, you are correct. Congratulations. The summation of all of the disks mr squareds, which is the summation of all of their individual moments of inertia, is equal to the whole compact disk's moments of inertia. So I here represents the total disk moment of inertia. Omega sub I, every single particle on this compact disk has the same angular velocity at any instant. So we can write this as just I omega. And there you have it, the formula of the day, which is angular momentum, L, is equal to moment of inertia times angular velocity. What we said in the last video is true about this angular momentum. It is still has the units kilogram meters square per second, and it is still a vector quantity. So in this case, it's we would call it negative by convention since this is a clockwise spin. Alternatively, we can use the right hand rule and curl our fingers around and our thumb points into the page. So meaning we could draw that like this, which is supposed to be how an arrow looks when it's leaving you, the feathers behind. Quick example, if we take a bowling ball here and consider it a uniform sphere and give it a spin in a counterclockwise direction when looking from above, then we have angular momentum L is equal to moment of inertia I times angular velocity omega. The radius of a bowling ball is about 12 centimeters. For mass, we'll use 7 kilograms. And let's give it a spin of, we'll go 4 revolutions per second. Then angular momentum is equal to I. I, we look up on a chart, I for a bowling ball, or I for a sphere, is 2/5 times mr squared. So in this case, we have 2/5 times 7 kilograms times 0.12 meters squared. This whole thing is 0.0403. That's kilogram meters squared. I'm running out of room here. Omega is 4 revolutions per second. We need to turn that into radians per second. So that is 4 revolutions per second. So we'll multiply that times 2 pi radians per revolution. And we end up with 25.1 radians per second, giving us a total angular momentum of 1.01. The units will be kilogram meters squared per second. So go find a bowling ball, give it a spin, and you will observe about 1 kilogram meters squared per second worth of angular momentum. The direction is counterclockwise. We could add a positive to that or use the right hand rule and thumbs up, so it'd be up on the diagram, either way. But I really just wanted to look at the magnitude of the angular momentum here. I'm going to end our discussion here on angular momentum for this video, but there are a couple more on the subject. It is a fairly abstract concept, so we will do a couple of more example problems. One of them will explain what we observed in class with the weights and the spinning chair, and another is one of my favorite problems in physics involving the collapse of a very large massive star into a neutron star. In a very short time, their diameters can go from millions of miles to around 10. I've shown it on a map here between 275 and 24, which is Telegraph Road. It is a fascinating subject, and we'll look at the problem along with the spinning chair problem next time. See you then. Britton out.